So today we'll be talking about turbulence. Turbulence is a new topic. It's a special topic, and let me just check again. Kai, could you quickly say that everything is okay? Can you hear me?
Fine from my side. Yep.
Okay. Okay, very good. Because it looked like my audio is not. Okay, nice. Okay, turbulence is something quite special, something we have not talked about before, and it will be one of the primary aims of today's lecture to make sure that you understand what turbulence is. Because when you hear in the media, for instance, or you read in newspapers, there are many different understandings of turbulence, and mostly, or in many cases, they're wrong conceptions of what turbulence is. And I have here on the first slide of our slide deck, I have an old painting from Japan. It's called the Great Wave of, what is it called? Great Wave of Kanagawa. And it's a painting that usually fluid dynamicists show when they want to explain what turbulence is. It's one of the first representations of turbulence. But we'll go a bit more in detail and discuss what elements of this old painting from 1860 somewhere, what elements depict the classical elements of turbulence. So first of all, I want to make sure that after this lecture you have a clear understanding of what turbulence is. Second, it's important to me that you have an understanding of when turbulence starts, what it takes to have an onset of turbulence, right? Not every flow is turbulent all the time. Not every flow is turbulent. There are certain criteria which make a flow turbulent or not. That's also something I want you to understand. And the third thing is that I want you to understand what the effects of turbulent flow are. Maybe you have a few ideas of what they are, and probably there will be a few effects that you have not been fully aware of so far. So these are the three main aims of today's lecture. Let's go on. This is the course schedule. Maybe it's worthwhile to look at this real quick. We have in the last 2 weeks, last two lectures, we have talked about potential flow theory, which was flow without vorticity. So flow that you can understand. Sometimes people also call it an ideal flow. That's a flow when the Reynolds number goes to infinity or viscosity goes away. That's a flow that works without vorticity and usually leads to flow fields without, flow without viscosity, which leads to flow without vorticity. Before these two lectures, we had 3 lectures of viscous flows, and one of them was on Stokes flow. And Stokes flow was sort of the opposite of potential flow. That was the flow where viscosity dominates so much that the inertia does not play a role. So Reynolds went to 0, or in the limit of Reynolds to 0. And then in between, we had this lecture, Viscous Flows 3, on boundary layers. And we'll touch boundary layers again, especially toward the end of today's lecture again. And boundary layers will be a very important element when we talk about next week about the aerodynamics. Because in aerodynamics, we will piece all the elements, viscous flows, potential flow theory, and turbulence together to understand what's going on in the flow around an object, what generates lift, what generates drag. Okay, so let's go back to the Great Wave of Kanagawa. Actually the year 1829. So what are the elements that we see here that indicate us that this is actually showing a turbulent flow? I would like to point out at least one element here directly on the screen. Let me switch over to this laser pointer thingy. Yes, just look at these little structures and look at their shape, how they're formed. And I hope you can see that there's some kind of a fractal self-similar structure, this little breaking up into smallest eddies is also visible on a larger scale, like about this scale. and these here. And then you have yet a bigger scale, like the bigger scale, the wave itself, and the smaller wave. So it's this multitude of elements which all look a bit like a wave by itself, but they're all pieced together. So it's a multi-scale structure. We have a large-scale wave, and we have smaller and smaller and smaller patterns which look like smaller and smaller waves, and all of them together, they create this full picture of a breaking wave. Keep in mind, a wave that is not breaking, so a smooth wave that you might have on a lake, for instance, is not a turbulent flow. Turbulent flows in waves are waves which are breaking, which have this white foamy structure with the small scales on it. Another element that, well, we don't really see it, but at least we can picture it if we look at the image, is the unsteadiness. Turbulent flow is always unsteady, and it's unsteady in a way that it's not periodic. It's unsteady in a way that it's unpredictable and chaotic. If you ever have been at the ocean shore and watched waves coming in, you probably noticed there's maybe some high level periodicity in the scheme, but at the end of the day, you can never really predict when the big waves are coming. Sometimes there's like 10 smaller waves and then one big one, and then maybe only 2 smaller waves and one big one. There's not really any predictability in this whole system. It's highly unsteady and it is chaotic. It's not only temporally chaotic, it's also spatially chaotic. Chaotic in the sense that the wave that we see here, the great wave here, does not have exactly the same shape as the great wave just on the right side of this picture, or the other wave, smaller wave here in front of the picture. So chaos in terms of temporal evolution, but also chaos, unpredictability in terms of spatial distribution. The third or fourth criterion I would like to point out here, turbulence is always something three-dimensional. You cannot have turbulence if you only look at two-dimensional flows. You might find if you type in two-dimensional turbulence in Google, you will find some publications, but this is kind of a, let's say, slightly esoteric academic way of looking at turbulence, and some people will debate with you if this even can be called turbulence. What we typically call turbulence is always a three-dimensional phenomenon. So we can see this, that even though in general, on a large scale, waves have a rather 2D character, right? You have a wave front and you have a wave crest with a certain elongation coming toward you. If you look at the smaller scales, which are typical of turbulence, there's always some three-dimensionality in it, which break up this overall large-scale 2D structure. The final thing I would like to point out on this picture, and now you really have to imagine yourself standing in front of the ocean, is what happens when you hear the waves, right? You know, when you stand at the ocean front, you always hear a lot of noise, especially if the waves are big. And where does this noise come from? Well, this is noise generated by the fluid motion. This is what we call aeroacoustics. It's acoustic generated by a flow. So it's noise of turbulent flow. So turbulence by itself dissipates a lot of energy, and this energy does not have to be, but can be dissipated into acoustic waves. So that we hear a loud noise of breaking waves is just a result of a dissipative process. Waves, turbulent waves or turbulence in general, dissipates a lot of energy.
Mr. Roberts, can I shortly interrupt you?
Yes.
It would be more easier for us, I believe, if you could share the slide at the same time you're talking. Then we have to split it on the screen. But thank you very much
for pointing it out. I was actually thinking that I was sharing the slide. Thank you. That's why I was a bit confused before. I thought something was wrong, but well, The Easter break was too long. I'm sorry about that. Didn't realize I didn't share the slide. I knew something was wrong, but didn't know what. Okay, I hope you can see the slide now. Can you?
Thank you, perfect.
Okay, so yeah, maybe back to the beginning. These are the large scales I was talking about, and these are the smallest scales, right? You have cascades of different scales. It's always like a wave within a wave within a wave within a wave. And this is a typical depiction of turbulence. Yes, and the last thing I was saying is turbulence is always something very dissipative. We're always losing energy in waves, in turbulence. Now, what are the other places where we see turbulent flow in our daily lives? Definitely, we have a lot of turbulent flows in geophysical flow systems. So, for instance, in the atmosphere, we have a lot of turbulence. So most atmospheric flows have a turbulent character. Maybe if you look out the window today, there's, at least where I live, there's some wind, and you see maybe you see some leaves fluttering, and that's typically a turbulent flow which makes them flutter in the wind. If you happen to see a smokestack somewhere in the wind, and you will see the plume of the smoke going up, and especially today when we have quite a bit of wind, the smoke is tilted, and you see these plumy structures, these cauliflower-like structures, moving in a rather uncoordinated way. Maybe overall, there's this overall structure of the plume of the smokestack, but in detail, on the small scales, you will see little turbulent structures, just like here in the Great Wave of Kanagawa. Where else do we have turbulent flows? Well, if you, for instance, look in a river and you see little eddies forming at the edge of the river, these are classical turbulent structures. Even if you open a water faucet and you see the water trickling down, maybe if you open it only very, very little, you see that the stream of water coming down is smooth, and usually you can see through it. It's very transparent. But as soon as you open the faucet a bit more, you will get more flow, and then usually you'll get a turbulent flow. The jet of water breaks up into complex structures. For those of you who smoke, if you hold a cigarette and you see the smoke coming up, if you're very, very quiet, no one talks, no air motion, it may be very structured, very laminar, but as soon as you say a word, as soon as you move a little bit, the smoke plume of your cigarette will break up. So turbulence is all around us. Most flows in nature, but also many technical flows, are turbulent. For you as biomedical engineers, it's interesting to understand that flows in the human body are usually not turbulent. Most blood flows are not turbulent. And it's actually even a sign of a pathology, or it can be a sign of pathology, if blood flow becomes turbulent. And we'll see a picture of that in a second. So let me go on to the next slide here. This is a classical picture of an experiment. This is a flow around a sphere. And what you can see so the flows come from left to right. What you can see on the right-hand side is a so-called turbulent wake. We'll come back to that. It has something to do with the flow, which is separating here at this point. And behind the sphere, in this separated region, the flow has a tendency to become turbulent. So we see that we have regions like out here where it's all pitch black. This is laminar flow here, and we have an inner zone of turbulent flow. So turbulent flow and laminar flow can be next to each other and be present at the same time. And the boundary between these two can either be rather rather clear and rather distinct, or as you see it back here, it can be rather fuzzy. It can be even difficult if you're like at this point to decide whether you're still in laminar flow or in turbulent flow. Again, typical characteristic of turbulent flow. Looking at this sphere, I would actually like to draw something on the blackboard just to indicate this whole concept of sphere, flow around spheres or flow around cylinders. We had this a few times. And one of the things that we had was, for instance, the flow around the cylinder in potential flow. Something we did, I think, last week or a few weeks before. And we saw that we had streamlines which go around the object more or less like that. And the velocity profile we obtain looked roughly like that. We had here close to the sphere, we had a slightly accelerated flow because the fluid is displaced. Yes, had to speed up a little bit, and then it goes out to the constant velocity of the outer flow with the oncoming velocity u. And we have a non-zero velocity at the wall, characteristic of potential flow. So that was the situation for potential flow, or ideally speaking, if Reynolds goes to infinity, if viscosity does not play a role. The other thing that we did was the Stokes flow. And in Stokes flow, the streamlines looked almost the same. They were also quite symmetrical or fully symmetrical around the sphere, except that the velocity profile at this point looked a bit different. So we have a no-slip boundary condition here. And then as you go out, we also go to the constant flow velocity. That was the situation of Stokes flow. Or the case where Reynolds goes toward zero. These are the two things that we looked at. This was the block on viscous or highly viscous flow. This was the block on ideal flows or flows where viscosity does not play a role. Now, what is it in reality? Well, the real story, what the flow really looks like, well, not always really, but at least for what we look at today, is somewhere in between, where we have, let me move over left more. Where we have a flow around a sphere, or let's say around a cylinder for that matter, at the Reynolds number, which is, let's call it finite, so neither zero nor going toward infinity, let's say a moderate Reynolds number. Maybe we better call it moderate, not finite. We'll have a few more slides where we talk a bit more about what Reynolds number I mean. Reynolds number moderate, maybe a few thousand up to 100,000. And what we will see in that case is this situation, or actually the situation we have on the slide. we actually do have a boundary layer which is rather thin, and we have an outer flow which almost looks like the potential flow out here. And the new thing that we have not had so far is a point about here, which is a separation point. But we also have one here, separation point. And here we have a turbulent wake. Huh? In front here, we have close to the wall, we have boundary layers. Which in the first place do not have to be turbulent, but they can be turbulent. So we may even have a case where we have a laminar boundary layer here and the turbulent wake, or we may have the case where the boundary layer is also turbulent and the wake is also turbulent. So these are two separate flow systems, and both can become turbulent, both can, well, yeah, actually also wakes can be laminar. They usually are turbulent, but boundary layers can be both turbulent or laminar. We have multiple flow systems in reality, and the case that we had before, either Stokes flow or potential flow are really idealized cases that we will only see in very special configuration. In reality, most technical situations that we encounter in reality will mostly show this picture. So we have seen now on the slide what such a turbulent wake may look like. We'll come back to that actually. Now, let me go back to the slide here. And I mentioned that boundary layers can also be turbulent. So for instance, here, I don't know, but I think on this experiment, this boundary layer probably was a laminar boundary layer. And you will see, hopefully before the end of this lecture, or definitely next week, why I think this is laminar. There's a way we can see that indirectly. But I would like to show you what turbulent boundary layers look like. So let's move on to this slide here now. So these are visualizations of turbulent boundary layers. So here you see a turbulent boundary layer from the side, where you see smoke entering into the boundary layer. So instead of having a classical boundary layer structure where the flow, like in the Blasius boundary layer, just has this smooth and steady profile, which is maybe developing, thickening as we go downstream, but essentially the flow is always pointing in downstream direction, is not fluctuating, is not chaotic, is highly structured. This can be superimposed by such structures we see on the left. Structures which are vortices of different scales, small vortices, big vortices, which interact in a chaotic, unpredictable, unstructured way with the flow. What you see on the right-hand side is actually a boundary layer seen from the top. So this is a boundary layer which is flowing from left to right over a surface, and we're looking from the top onto this surface. on the very left, this boundary layer probably starts as a still very laminar boundary layer. And someone introduced some disturbances, probably with some roughness elements, into this boundary layer. And that's probably where these little lines are starting here. And eventually these lines, they become bigger and bigger disturbances until you have something quite turbulent in this range here. Probably farther to the right, the turbulence stops again. So turbulent boundary layers by itself is a rather complicated situation. And I would like to show you a video here, which comes from a numerical simulation of a turbulent boundary layer, and should show you the complexity of here. To give you an impression of the complexity of such a flow. Huh? So the little structures we see here are visualizations of vortical structures. These are little vortices inside a boundary layer. So this is a flat plate. We're now looking onto a flat plate. Flow is now coming from left to right. We see at the far left, or now at the back, where the structures are starting. So this is like where the little perturbations are starting, and they're quickly evolving into these structures which are red on top and which become more and more turbulent. You see now back here, they really break up. In the beginning, the structures still had like this round, pointy shape. They're called hairpin vortices. Now they're completely broken up. This is a fully developed turbulent flow, a thick boundary layer which has small vortices, bigger vortices, but vortices of all scales. See, from the left all the way to the right, the boundary layer is thickening up, and it's mixing with all these little vortices. I think this now, maybe that was it. Yeah, okay. So you see how complex such a boundary layer can be. You stop here. And this is not only the case for boundary layers and not only the case for wakes. So we have seen wakes, we have seen boundary layers, can also be the case for free shear flows. To this end, let's go back to our slides. The next slide we have here. Yeah, it's a turbulent shear flow. That's also a numerical simulation. What we see on the left, we see a nozzle of a jet, or let's say a nozzle and some fluid coming out of this nozzle. And this flow very quickly develops into a very, very chaotic, very, very turbulent flow. So this is not a boundary layer where we have a wall on one side. This is a free jet. So imagine this could be a jet engine of an airplane. This could be the jet engine of an airplane issuing hot air into the free space, and we'll have a very quick breakdown of this structure. What you actually also see, let me play this movie again. What you can also see later in this movie, how these turbulent structures, how they're fluctuating in time, how they can generate sound waves. These are then these dark structures. I think these are pressure isosurfaces, so local pressure oscillations. And later in the movie, I think we'll see, not yet, we'll see acoustic waves radiating from the structure. Yeah, now we see them. Huh? So what you see here, these are acoustic waves radiating away from this turbulent flow. This is a classical, canonical problem of aeroacoustics, how an airflow can generate sound emissions. I mean, you all know that from an airplane taking off can be quite loud, and part of this noise is not just from the combustion of the jet engine, it's actually from the jet coming out. All connected to turbulence. Next example. This is turbulent flow inside the body past the bioprosthetic valve. It's also a numerical simulation. What you see here is a structure. Well, this thing here is the ascending aorta, or a model of the ascending aorta. Down here, you have a heart valve. It's a bit difficult to see, maybe go back again. Here, it is a bioprosthetic heart valve, a device that is implanted, and it can create complex flow structures. Again, we start off with rather large eddies in the beginning, and as we go farther downstream and farther down in time, these eddies break down and become smaller and smaller vortices, very, very small structures, which are characteristic. This here on the right-hand side is actually an analysis of the same flow. It's just showing one slice through a flow field. And what we do see is actually measures amplitude of fluctuation. So we subtracted a mean flow. There's a mean flow. And if we subtract that, we only see the oscillations on top of the mean flow. And that gives us a measure for the intensity of the turbulence. We'll come back to that next time. You see, this is like one of the cases where flow in the human body, blood flow, can become turbulent, which may be pathological, may create some problems. Why is this a problem? Let's study this a little bit, because I think it's important for use by medical engineers. Why is turbulent blood flow not necessarily a good thing? Well, there's at least 3, maybe 4 reasons. One of the first reasons to look at is that these small scale eddies, they lead to local shear stresses, local shear forces, which act on the blood particles. And this can actually lead to blood trauma. It can maybe damage red blood cells. Usually turbulence is not that strong, but what it definitely can do, it can activate thrombocytes. So thrombocytes are those blood platelets, blood particles, which are responsible for the coagulation cascade. And if you activate them, it may lead to the formation of thrombi. So turbulence may induce thrombus formation. This is why we should look out for turbulent flow, make sure it's not, if it's there, it's not too intense. What else is problematic? Well, we'll learn later today that turbulent flow is always connected to energy losses. I already mentioned this in the first picture with the wave. So we have extensive or higher energy losses if we have turbulent flow as compared to laminar flow. What does this mean for the heart, in this case of the heart valve? If we have strong turbulent flow, we lose more energy to turbulence, so the heart will have to work harder to produce certain blood pressure downstream. So that's the second problem, why turbulent blood flow may not be or is actually not a good thing for the human body. What is another problem? Well, another problem is the interaction between turbulent flow and the wall of the ascending aorta, or of any arterial wall, if you like. You probably know from anatomy that the innermost layer of a blood vessel is called the endothelium, and the endothelial layer is highly sensitive to shear stresses, to mechanical forces. And these mechanical forces are exerted by the bloodstream. If the bloodstream is laminar, the endothelial cells actually like that, and they develop in a nice way. If the shear forces acting on the endothelial layers are chaotic or turbulent, so to speak, they will not like that, and it will actually damage them, and you will get a higher turnover. You may get lesions of the endothelial layer, and lesions of the endothelial layer is usually the starting point of any inflammation process leading to atheromata, so plaque formation, or let's say aneurysm formation, or aortic dissection. So turbulent flow is also not good for the wall. And last but not least, turbulent flow can act on the soft tissue structure you have here in the heart valve itself. So imagine you have a valve leaflet, which is a material made of a thin tissue material, usually pericardium, and you constantly have these chaotic stresses working on this leaflet. It's a bit like a flag fluttering in the wind. And if you have seen flags that have been fluttering in the wind for, I don't know, months or maybe many years, they usually wear out and disintegrate or deteriorate structurally at their end. And that's exactly what can happen to the structures. So overall, this is the reason why turbulence in blood flow is usually not a very good thing. And it's up on us as engineers to learn how to prevent. Okay, but let's get this into all this a bit more in a structured way. There's a concept known as laminar turbulent transition. Laminar turbulent transition is the name of the mechanism or of the process which takes a laminar flow toward a turbulent flow. We see this here depicted in a very classical numerical experiment for a Blasius boundary layer. So you have a Blasius boundary layer. Hello? Oops, sorry. There was just someone talking instead of me. Hope you can hear me again. So there's a flow coming from left to right, entering here on the left end and exiting on the right hand side. It's a Blasius boundary layer. And what we do start off here is with this yellow structure on the left hand side, this yellow structure, which is an initial perturbation. So the person who did the simulation actually added this as an initial perturbation. It's like a little kick to the flow. And what you see here, what is happening with the structure that moves downstream with the flow, that its two-dimensional structure starts breaking up into a three-dimensional structure. It starts bending, it breaks up in two pieces, eventually forms these red structures. Maybe you remember them from seeing them before in the video. This is one of these hairpin vortices. And then eventually it breaks down in this white region into very complex structures. You can't really make out anything coherent anymore. And this is still called the breakdown phase. And here to the far right, we then have fully developed turbulent flow. So everything from the left structure, yellow structure, all the way to the green structures, this is what would be called the transitional phase, where we're transitioning from laminar to turbulent flow. Usually, we only see either the green, fully turbulent, or we see what is to the left of this domain, which is fully laminar. This transition phase usually is quite hidden, it's difficult to see, and only in numerical simulations like these, it can be depicted stage-wise as beautifully as that. If you look the same story, if you look it up in a textbook, you'll find pictures like these here. This is a classical textbook representation of how such a transition looks like. It's a boundary layer transition, but overall, on a large scale, the story is the same also for other flows, like for jet flows or for waves. This is the classical transition process where we start off on the left with a laminar boundary layer and we end up on the right with a turbulent boundary layer. Now, is there a way to classify why the flow should be turbulent on the right-hand side and why the flow is not turbulent on the left-hand side? Now, if we think back of how we described boundary layers and we had this thickness increasing, and what we did back then is we identified, or let's say we defined, a Reynolds number. We actually defined a boundary layer Reynolds number which increased in downstream direction. That was this Ray X. Let me quickly write it down on the blackboard again, just that we remember it. So as we have the boundary layer on a flat plate, developing in downstream direction, in the X direction, we have a thickness delta, which we knew it increased with the square root of X. And we defined a Reynolds number. So here's an oncoming flow with velocity U. We defined the Reynolds number U times X divided by the viscosity U. This was our Reynolds number X. This is how we classified the boundary layer at different positions. So essentially, what this Reynolds number is doing, it's starting from 0 and increases as we go downstream, as the boundary layer becomes thicker and thicker, we are going into a higher and higher Reynolds number. And what we have seen on the picture on the slide before, that there's a certain point as you go downstream where the flow becomes turbulent or starts transitioning and then becomes turbulent. So apparently, it must have something to do with the Reynolds number. There is a certain critical Reynolds number we'll learn. There will be somewhere a critical Reynolds number, Ray crit, beyond which the flow has, let's say, a tendency to become turbulent. If we're before, or let's say below this critical Reynolds number, it does not become turbulent and will remain laminar. Go back to the slide. This is also shown here at the bottom of this diagram. We have the Reynolds number increasing from left to right. Below a certain critical Reynolds number, the flow will always remain laminar. In certain special cases, you can even show this mathematically, that there's no chance, in a rigorous way, there's no chance for the flow to become turbulent. Beyond this critical Reynolds number, the transition process will set on, and after another Reynolds number, we have fully developed turbulent flow. It's a very classical picture along the ray of the Reynolds number. And it was actually Reynolds, we saw this picture a few times now, it was Reynolds, Osborne Reynolds, 1883, who already found that out. He didn't really describe it that way, but more or less that's what he did. He ran an experiment of pipe flow, right? He had his pipe here in his apparatus, and he had a little line of ink, of black ink, to visualize the flow, to see what the flow looks like. And he found laminar flow, but he also found turbulent flow. And he found turbulent flow when he either increased the velocity or used a bigger pipe or decreased viscosity. And what we know now is the ratio of diameter of velocity divided by viscosity, which is the Reynolds number. That's really what determines whether flow will be turbulent or whether it will be laminar. In the boundary layer, it's the Reynolds number built with the downstream direction X, the Reynolds X. For pipe flow, it's the Reynolds number built with the diameter of the pipe. Right? So the way the Reynolds number is defined is slightly different depending on which flow we're looking at, but overall, it will always be this basic concept that there's a critical Reynolds number which splits the world into a laminar world and a turbulent world. And we should also be aware that this border, this critical Reynolds number, is not always an absolutely sharp edge. It can be quite a fuzzy edge. For instance, for pipe flow, we have a situation that if you look it up in books, many books will talk about Reynolds numbers, critical Reynolds numbers of 2,300. And I deliberately did not put this number here on the slide because the Reynolds number of 2,300 may be true for many, many cases, but there are experiments that have been done which show that it can also maintain under certain conditions laminar flows for much higher Reynolds numbers. So that's a bit of the unfortunate thing. It's a mathematically rigorous concept, but there's no way to give this very, very sharp single Reynolds number. But we can certainly say if Reynolds numbers is 1 order of magnitude beyond the critical number, it's very, very likely to be turbulent. If it's 1 order of magnitude below this critical number, it will very, very likely be flat. So let me summarize what we have said about turbulent flows so far. And this is a slide which somehow tries to summarize what turbulence is. So I took actually the first sentence out of a book. Turbulence is a dissipative flow state characterized by nonlinear, fluctuating, three-dimensional vorticity. So it has a lot of words in it, this sentence. Let's take this apart. So one of the important words in this thing here is the fluctuation. Turbulence is always fluctuating in a irregular, chaotic, and unpredictable. There's the word nonlinear in it. What does it mean, nonlinear? This is a mathematical term. We should now go back to the Navier-Stokes equation and remember what the Navier-Stokes equation looks like on the left-hand side. On the left-hand side, we have the unsteady term, the du dt term, and we have this nonlinear term, the u times nabla u. And that's a nonlinear term which mathematically creates problems. And when we looked at Stokes flow, we saw that for small Reynolds numbers, this nonlinear term can be neglected, can be simplified, can be assumed to be zero. And for larger Reynolds number, this term gains an importance. And it's exactly this nonlinear term what makes, in a mathematical sense, turbulence possible. And this term will only be strong enough if the Reynolds number is large enough. The small Reynolds number will strengthen the viscous term on the right-hand side of Navier-Stokes and relatively weaken the nonlinearity. And for large Reynolds numbers, the viscous term will be weakened, which indirectly strengthens the nonlinear term. Third term we have in this sentence is vorticity. Obviously, we always see streaks, we see eddies, we see complex vortical structures at multiple scales. Dissipation, I already mentioned that. We always have a lot of energy transfer from large scales toward very small scales, and there we have a dissipation into heat, can also be into sound waves, and so on. Finally, and that's something we have not really talked about yet, turbulence also has the character to increase diffusivity. Not only dissipative, but also diffusivity. So what does that mean? Turbulent flows are not always bad in a technical sense. There's also certain technical applications where we're looking for turbulent flows. And that is the case where we want to increase the heat transfer or where we want to increase the mixing. So mixing of species in chemical engineering, when we have two fluids with different species and we want to mix them, it's much more efficient to have a turbulent flow to mix them than to have a laminar flow and only to have like a classical dissipation to mix this flow. Same thing is if we want to, let's say, have a heat transfer, we have a hot water pipe and we have fluid around it, and we want to heat up the fluid around the hot water pipe with the heat from the water pipe. If we have a turbulent flow around it, the heat transfer is much more efficient than if we just have normal thermal transport, which has a diffusive. So these are the main characteristics of turbulent flows, and I think this is a good point now to take a break until, what time is it? Yeah, let's say until 1/4 past, and then we'll continue. Okay.